Okay. Okay, let's see. Okay. Settings, I think I am good. Yeah, 48. Beautiful. Just make sure the chat's there. Ah, nice. Okay. There we go. Docs, stats. Okay. Nice. Okay. I think it works. That is beautiful. Okay, sweet. Now let us actually, I guess, get started. So, okay, there we go. Yep. So, okay, so on my desktop today, let me just kind of set the stage for what we're going to be building. Basically, we are going to be building a very, 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 very basic math expression parser. We're not going to build the evaluator probably today, but the parser. And that's important because that's the hardest part of the whole programming language thing. So let's kind of show an example of what we want to be able to do, right? So if you just type in node in here, you'll get a REPL. So we could type in like 10 and we get back 10 because 10 is a valid expression. So the expression 10 semicolon is valid. The expression 10 plus 2, we would expect 12, and of course that's what we get. And this is basically the goal of what we want to build. We want to be able to do like something like 10 plus 3 times 4 minus 5 and get the correct response back. And this seems pretty simple. You may think regular expressions or similar autonoma will help you achieve this result. And yes, you're true. Regular expressions could get you pretty far with this kind of thing. However, when you start adding depth, like 10 plus 2 minus 30.4, something like this, this is something a regular expression actually can't help you with. So our goal for today's stream is going to be to actually just make a parser ourselves, and we're going to be doing it in the beautifully annoying language of JavaScript. So I'm going to create a directory, and I'm going to call it JS parser, and we're going to cd into JS parser. Okay, I'm going to touch a lexer dot, not cpp, what am I doing, dot .js, and touch a parser.js file, and touch a main.js file. So I'm going to just open these all up in Visual Studio Code. Okay, there we go. So now that we have it all in VS Code, this is actually great. We want to basically start in the main, and what I'm going to do is I kind of want to lay out how I want this to work, right? So again, we want some sort of expression or code to be parsed. So let's just say our expression or our maths is equal to 10 plus 2. Right? Let's say this is what we want to be able to parse, right? And let's say first things first is we want to think what does it mean to parse a structure like so, right? What does it mean to take this string into something that we can then later evaluate and do things with, right? And what you can kind of think of is, I'll just open up the comments and write the expression 10 plus 2 being maths. You can think of it maths. Let's just put up here. I'm going to try to build a tree, right? So I don't know, like that, right? No, there we go. There we go. So you can kind of think of it like this, right? Where it's a tree where we have a plus operator, right? So maths is basically this. We have maths. Where's the pipe symbol? Where's the pipe symbol? Am I missing something? There we go. I'll just do semicolon. I actually forgot where the pipe symbol is. Oh. Vertical pipe. Okay, whatever. You get you get the point. Where basically we have something like this, right? Maths, and we want to say that there's basically a plus operator, right? So you can think of it like this. We have maths, right, is the result of some sort of expression. So we want to build this tree-like structure where we could say maths is a binary expression. So let's say a binary expression. And what is a binary expression? Well, binary, we're not really thinking in terms of zeros or ones. We're thinking in terms of two operands, right? So 10, a plus or an operator, and 2. And the reason it's called a binary expression is because there's two sides, right? You have one side, the operator, and the second side. This is a valid binary expression, 10 plus 2, or 10 plus parentheses, where inside of this parentheses, 3 minus 4 is another binary expression, right? So this is where we can get these really complicated but very neat tree structures. So let's just go back here, 10 plus 5, right? Binary expression, and we want to know, well, what is the binary expression, right? Well, we want to basically have some sort of object or tree where we could say, well, this is a binary expression, which has like a type, we'll give it. And it'll basically have an operator, which is going to be plus. The right side is 5, and the is 10, right? And this is our valid binary expression, basically. This is what we want to create with this whole entire thing, right? So we want to take this basically expression and convert it into something like this. And simply put, this just looks like this, right? So you have plus 10 and 5, right? This is basically what we want to create. Just this kind of thing, right? So we have a tree where the operator is plus and the operands are 5. Now let's imagine we have a more complicated instruction like 10 plus 3 plus 1. Let's just do a minus, so we have 3 times, right? So now we have this complicated structure where we want to do 10, right? So this is fine, 10 plus, but instead this is no longer this. This is another binary expression. So how do we structure this, right? Well, we could say this is a minus, or a multiply, sorry. There we go. Where we say this is now 3 and 1, right? This is kind of our tree layout. You can kind of see how this expression up above, let me get rid of this, is what we're creating as a tree. We're saying this is what our tree is going to look like. We have a binary expression where the left-hand side is 10, and the right-hand side is another binary expression. So this is literally it. This is what we want to create by parsing this type of syntax. And the first step to this is actually doing something by creating a lexer. And a lexer is a fancy way of saying take this string and convert it into an array, basically, of characters slash tokens, right? So we could say this is a number token, right? The number 10 is a number token. There's a white space token, which we'll just ignore. There's a plus token. There's a parentheses open token, a 3 token, a times token, a 1 token, and an end parentheses token. And this is going to be important because later on in our code, we're going to want to iterate each token by token and say, okay, what is the next token? Is it a plus? Okay, I had to parse the tree. Is it what, right? Is it a parenthesis? Okay, I had to create another tree, And that's basically why we had to do this lexing phase. It just makes it a lot easier. So enough kind of, yep. Thank you, Alvaro. Alvaro, yep. So yeah, we're talking about ASTs. I'm trying to give an explanation. But yeah, that's what we're going to be doing today's episode. We are just going to be converting a syntax or a expression like this and getting a working AST that also correctly follows order of operations, right? Because we would expect if we remove these parentheses that this side of the tree would have precedence, right? So if you imagine this, there's kind of two scenarios here. You could have the left-hand side, like so, where it evaluates the 10 plus the 3 times the 1, which is the correct precedence, by the way. Or we could have this kind of precedence, where we have, we would have plus 10, and I think this would be 3. Or no, this would be, what would this be? The incorrect precedence would be, oh, sorry, it'd be multiply. There we go. Yeah, it'd be multiply 10 plus, right, 10, 3, and then this would be 1. So this would be incorrect precedence, but this is another way you can kind of get this, and we want to have correct precedence. So enough rambling, I'm going to actually get started, and let's create a lexer class in JavaScript. So if you want to follow along, or follow along with the video, because it's just me and Alvaro right now, you can do so. So let's go into our lexer.js file, and in here, we are just going to create a class and call it lexer. All right, and I'm just going to export class lexer, like so. Beautiful. So we have our default class of lexer. I'm just going to import it in here, like so. Import lexer from lexer. Okay. So we have this lexer class, and as I said earlier, our goal is to get this string and go token or character by character to produce a token. How's it going? Good night. Good night, man, if you're not able to follow along. Yeah, it's pretty late for a lot of people, sadly. So in here, we're going to have a couple parameters, right? We're going to want to be able to store, and I'm going to use this hashtag syntax in JavaScript, which allows us to declare a private variable, if I remember correctly. What we're going to want to do is inside of here, we are going to take in the stream. I'm just going to set it to a default string, right? And Arthur here. Arthur. Oh, Arthur. How's it going, man? How's the app coming along? And then we're going to also have a cursor, which we're just going to set by default to being 0. So we're saying our string is of 0 length. So that's basically it for this. We are going to want to create a function, which is going to, well, create an AST. So we're going to do tokenize. I think I'm going to just do this. Yeah, there we go. Okay, so tokenize is going to take in a string, which we're just going to call input. I'm just going to set it by default to an empty string. And what we're going to want to do is say stream, this dot stream is equal to input, and this dot cursor is equal to 0, because the cursor we want to start at 0, right? And what we're going to want to do is inside of this tokenize string, we're going to want to build our tokens. So to do that, let us actually, in here, create a while loop, because we want to iterate over every single one of these tokens. And this is important because we want to iterate over every character. So we're going to do a while the cursor, which is basically our position in the string, is less than this dot stream dot length. Basically, continue until there's no characters. Okay. So while there's no characters, we're basically going to want to run a switch or an if. I'm just going to do an if-else block, but you could also be doing a switch chain here. And we're going to continue through every character and check the character for a couple different things here, right? So what are the things we have to check for? Well, we want to look for symbols that are like plus, multiply, divide, maybe modulus, things like that. You want to check for numbers. And for now, let's just start with those. And let's kind of handle that. So first things first is we don't really care about the pluses. Or the white spaces, right? Like this has the exact same meaning as this, right? They're the exact same meaning. So we don't really care about the white space tokens. So let's actually skip those. So we're going to do if I'm also going to create a helper method, also called current. Current is going to just return this dot stream of this dot cursor. And I'm not doing any checks to make sure that we're inside of the bounds of the string. I'm just going to assume that this is valid. Also, I did not define the function in the right location. There we go. I'm getting an error somewhere. Oh, okay. If current, so we're going to want to do if this dot current, right? So this is going to get the current character. I'm actually going to call it ats just for brevity's sake. We'll call it ats. If at is equal to a backslash n, right, would be a new line. We're not going to really care about that. We're going to say if it's equal to a space character or this dot is equal to a backslash. That's actually it, really. We don't really have to check for any other characters. I'll do backslash s or backslash t. There we go. So we're going to check for a space or a tab character, and if we find one of those, we're simply going to break. Actually, we are going to. I'll do this in a switch. I'll do this in a switch. So we're going to take the at, right? This dot at. Okay, so if the value is of a space, I'm trying to show how to use these without doing regular expressions. For example, say you're writing this in a language like C, which is actually what I'm writing my language in now, how we can kind of go about this without using regex, because for something like this, we're only really looking for a few cases. So we're going to look for a case of a space and case of a backslash n, case of a backslash s, backslash t, all those kind of things, right? So if we get any of these cases, we're just going to break out of here. And that'll actually put us into the end of this kind of area where we're just going to do this dot cursor plus plus. But yes, I do at Varo. That is obviously exactly what you'd want to do. Use a regular expression, especially in JavaScript. I'm just kind of showing the least JavaScript-esque, modern language thing, right, of what you do. But I think it's good practice. So you can see, okay, at the current character, we don't have a space or a t or any of those, right? So we've already handled 1/3 of the types of characters. Next, we want to handle these symbols, right? A plus, multiply, divide, and minus. So let's actually check for those. So we're going to do case. If we find a plus token, right, what do we do? Well, what we're going to want to do is actually keep track of some sort of array of tokens, right? So I'm going to have a const tokens is equal to just an array, like so. And I'm also going to create a little object or a function called createToken, which I'm just going to put in here. Actually, we don't even need that even. But in here, we're going to handle our plus token, right? So what we want to do is if we get a plus token, we are going to basically add to this tokens array that we have a plus token. So we're going to do tokens.push, and I'm just going to do an object, and what we're going to say is a token has to have some sort of type, right? We want to know what type of token this is. So this is just going to be I'm going to create a constant to kind of organize this a little bit better. So up at the top, I'm going to create a constant token types, right? And I'm just going to set it equal to this. And what we're going to do is we're going to have a plus is equal to plus is equal to 0. Oh, no, I can't do that. Yeah, plus is equal to 0. Minus is equal to minus do this. Plus minus multiply and divide. And divide. And then we're going to also want to have 3 other types of tokens, right? We're going to want to know when the token is a numeric, right? A number. We're just going to handle integers, so I'm just going to call this integer. And this is going to be integer. And we're also going to want to handle left parentheses as well as right parentheses. But for now, we're just going to handle these 4 types of tokens. And eventually, we're going to need an EOF token for an end of file token, which just says we're at the end of our file. So I'm just going to create that right here, right? So we have this token types constant where we can now do something like type is token types dot, it's going to be a plus token, right? And in here, we're going to have the value of plus. It doesn't really matter. We're never going to actually use this value, so I'll actually get rid of that. But typically, you'll want to have a value, so to keep it somewhat consistent, we'll do this. So we're saying if we get to a plus token, well, we have a plus, right? So that makes sense. And then we're just going to break. And let's do the exact same thing for the remainders, right? So minus, we're going to have a token type dot minus. It's going to be a minus token. I actually don't think we'll need the break in here, so we'll get rid of that so it cleans it up a little bit. Okay, so we're going to have a multiply and a divide. Divide, multiply, and this is going to be token type dot multiply, and this is going to be token type dot divide. Okay, there we go. So in here we have already handled our plus, minus, multiply, divide, and white spaces and things like that. So now what we're going to have to handle is numeric values. Hey, how's it going, man? So, how's it going, Fizzy? So, now that we've already handled the plus token, minus token, multiply token, and divide token, we have to think how, without regular expressions or using a function in JavaScript that just checks for an integer, how would we check to see what a numeric value is? And a pretty simple way of doing this is by actually using the character, right? So we know that this is a character. We can check the ASCII character and see is it of type number, right? And the way we kind of do this is we're just going to say this is going to be our default case for now. What we're going to do is in here, we're going to check for numbers, right? Check for a numeric value. And we know that we're only dealing with integers, right? If you were actually doing this without integers, you had to factor in the decimal place and things like such. So let's actually just work with integers for now, keep it simple. And what we're going to want to do is say, okay, I'm going to create a function called isNumeric. Not numeric literal. We're just going to do if is numeric, not numeric literal, TypeScript. There we go. And we're going to pass in our this dot at, right? So this dot at, which is going to get our current token. And we're just going to say if this is a numeric literal, or a numeric, right, we're going to build our numeric token. Else, at this point, let's just throw an error. Actually, we'll do that. Yeah, we'll do it here. So if it's not a numeric, let's just throw an error, right? Throw new exception, throw new error. Oh my god, I have not written JavaScript in a while. Okay. Expected eval token at position. I'll do this in template strings, right? And we'll just pass in the this.cursor. There we go. Okay, so if we didn't get that, right, we're going to throw an error. But let's actually write this as numeric function, and we'll quickly get on with that, right? So I'm just going to close that down a little bit, and we're going to write our isNumeric function is numeric value, right? It's going to take in a character. I'm just going to say char. And we're going to take in this character and check if it is a numeric value. And the way I'm going to do this is I'm just going to open up Chrome real quick. And we're going to check if this value is, sorry, to open Chrome. Okay, we're going to go to a ASCII, ASCII table. And we're going to go to ASCIItable.com and actually check and see if we have a numeric character. And the way we can kind of read this is, well, numeric characters are, there we go, they start at value 48 is the decimal value. So 48 is 0, and they end at 57, which we know is 9. So we can say if this ASCII character is 48 through 57, then we know we're at a numeric. Else, we know we're not. So that's actually what we're going to do. What we are going to do is we're going to say if character dot because we could do the parse int, right? We could parse this and see if this character is a number, but in C or languages like that, you won't have that ability to do that. So we're going to do car. I'm going to just set this to a string and get some IntelliSense. So car dot char code. No, is it dot char code at 0, right? Because it's one character, is equal to, and we're just going to pass in the number because we know it is 48 for 0, right? So we're going to say if it is greater than or equal to 48, or char.charcode at 0 is less than or equal to 57, then we're just going to return this, right? So we're going to return, there we go. So we're going to say return if it is greater than or equal to 48, or if it is less than or equal to 57. And this will tell us if the actual character we're looking at is numeric. Pango, yeah, I will be uploading this as a video later, for sure. And I hope that makes sense. We obviously could just do like parse int, right? We could say like if parse int of char, and then do the inverse of is not a number, right? And that would do the same thing, but in this case, I want to check the actual character and just return like that, right? So in our tokenize method, we now can say, okay, if we're at a numeric value, we know that we're at a numeric value, right? So that's perfect. We can actually start building our number. And I'm going to do this by constructing a string. I'm going to call it my str number is just going to be equal to this dot at, right? We're just going to take this and kind of construct it as a string for now. What we're going to do then is we want to basically iterate, right, until we're not at a number. And that's basically what we're going to do. We are going to do while inside of this, remember, we're still here. We haven't incremented the cursor, nothing like that. What we're going to do is, I'm just going to actually set this to a blank string by default, is we're going to do while is numeric this dot at, right? So we're going to check the current character while this is a number, and we're also going to make sure that this dot cursor is less than this dot stream dot length, right? So we're going to say while we're still inside of our string, and while our current character is still numeric, we're just going to do str. We'll do it like this, I guess. str number dot plus equals, right, this dot at, like so, and then we're just going to do this dot cursor plus plus, which means now our next character, right, is going to be the next character. And then once we know we're doing that, right, once we know that we have successfully iterated through this entire thing and gotten a number or a space or something like that, once we're finally there, we can actually convert this to a number and add a new token. So what we're going to do that is actually do parseInt. And the reason I'm not doing it while checking the number, right, is because in C++ there are functions for parsing numbers, like STOLD or STOLLD or STOID, or STOI, right? And I didn't want to do that for checking, but for parsing, I'm just going to go ahead and do that. So we're going to do tokens.push, and we're going to do our type, right, is of token types dot, and we're going to do our integer type. And then we're going to say our value, right? Value is our number, right? And we're going to parse it. So we're going to do parse int of str number, right? And now we have pushed on our token, and our current cursor at this point in time is going to be on a white space or a character that's not a numeric value, right? So what we actually want to do is decrement the character once we get right here, because currently, right, if you imagine our string being something like this, 10 plus 45, right, minus 3, you would notice that if we were starting here, we would start 1, right? 1 is numeric. Cool. So now we're in here. While 1 is numeric, perfect. Add 1. So this would then become 1. Our cursor would go to here, and it would say 0 is numeric. Perfect. Right? We're at 0. And then what will happen is we're going to increment this again. So now, while this white space character is numeric, and this is going to fail, the white space character that we'd be at right here is no longer numeric. It can't be, right? So what's going to happen, though, is it's going to push on the token, and when we pass, it's going to skip past this white space. So now we'll be at a plus. This is fine in this case, but imagine if we didn't have that white space in there. What would instead happen is we would go, okay, we have our 10, right? We've pushed on that, and now our next character is a plus. Plus is not numeric, okay? But then we're going to skip past the plus token, which means when we get back up here, we won't know it was there. And that's going to be an issue. So what we're actually going to want to do is just do this dot cursor minus minus. And this is going to put us 1 token back from where we are now, which means when we advance here, we're at a token that we know is no longer a number. So that's why I'm doing this dot cursor minus minus right here. Okay. So let us actually look and see what we actually get out of this, because this should, as far as I'm aware, if I didn't miss something, which I probably did, this will work, right? So we're now going to return tokens, just like so. And the last thing we're going to do before actually returning the token is we're going to do this dot tokens. No, this, oh no, it's just tokens. Tokens dot push, push, and we're going to do type is equal to token types dot EOF, right? And the value is going to be like so. So we're just saying this is our end of file or our end of line, right? We're just hard coding the value. But typically when parsing a language file, right? Because again, this is why we're doing this. There will actually be some end of file, and you want to know where that is for parsing. So we're just saying, hey, we're at the end of the file, right? We're done. And let's actually test this out and see if this works, right? So we have exported our lexer. I'm also going to export the const token types, and this should now be callable inside of here, right? So let us do this, right? We're going to do const tokens is equal to, we'll create a lexer, right? So we're going to do is equal to a new lexer. We're going to do lexer dot tokenize, and we're going to pass in our string of maths, right? We'll actually just pass in the string right here. So we'll do 10 plus 35. We'll do a minus, and then we'll add in a whole bunch of spaces and do 3, and we'll see if this parses correctly. So what we would expect to get back when logging, so we can do console.log tokens, right? What we expect to get back is an array where we have a token for the number, a token for the plus, a token for the 45, a token for minus, and a token for 3. So let's actually see if we get this back. So I'm going to, in here, we're going to test to make sure that this correctly parses 10 plus 3 times 1. Oh no, not that, sorry. And let's actually make sure we get a 10 token, a plus token, 45 token, and a minus token. So let's do this, right? So we're going to do node main.js. Import cannot be used outside of a module. Ah, yes, it is because I am using whatever this is called. We'll just switch it to an ES const lexer equal require. I don't actually remember how to use non-modules, if anyone remembers. There we go. And we're going to require, there we go. And here we are going to just export everything. Do module.exports is equal to lexer and token types. There we go. Okay, so what we'd expect now is to see our tokens, and we run this and we get lexer is not a constructor. Okay, that's good to know. Const lexer import lexer is equal to require lexer. I think I'm doing this right. Lexer is not a constructor. Am I missing something here? Module.exports is equal to lexer class of lexer. Oh, it's because I didn't have a constructor. I see what's going on here. Let me just set it. Let's say. I think this will actually work. Lexer is not a constructor. What am I doing wrong here? Const lexer. Can I just like console log lexer? Console log. What do we get back? Oh, okay. We get. Oh, I see what's going on. I'm not. Haha. Ah, there we go. Okay. So now we actually can run this and barring any errors, beautiful. Oh, almost. Okay. So when parsing this, we get this. So we get our type of integer of 10, but then we get value is 10, 10, and then 2 EOFs. Okay. That is good to know. So let us see what I did wrong here, right? So we're getting 10 plus, we're totally skipping everything else. So let's actually look and see what I'm doing wrong. Let's go into the lexer and kind of see what's going on here. So while the current token is here, let me break. I don't think I need to, but I don't know. I haven't written JavaScript in a bit, so this might be it. Try to implicitly break. And I'm just going to console.log when we get to this defaults, le.log, this.at. There we go. Now let's just see what we get. Okay, so we get the number 1, which makes sense, right? So we get if numeric. Oh, it's because I'm putting in the value of 10. That makes sense there. Yep, so we get the value 10, type EOF, value EOF. Okay. So we're getting here. Let me actually console.log this.stream. This.stream dot of this. Actually, I'm just gonna do this dot at. And let's see where we're at right here, right? So 1, 3. So when we get here, it looks like we have a 3. Do I even? Oh, fascinating. Percent. Well, this dot cursor is less than such link. Let's see. Okay, so while this is a numeric value, this dot cursor plus plus push integer value is a parse int of parser number, and then here let us console.log this dot cursor. Let's see what we get. 16. Ah. And I think it actually might be because of this. I don't. Let's see. So we get to 7, right? So 0, 1, 2, 3, 4, 5, 6, 7. While is numeric this dot at this. While is numeric. Let's just see what we're getting here. 49, 49. Okay. 0, 1. Yep, that makes sense. Debugger, and wouldn't you use debugger and breakpoints? Typically I actually don't with VS Code and JavaScript. I probably should get in the habit of doing that. I kind of am just looking at this and seeing why it's skipping something. I'm just not seeing what it's skipping. Break cursor plus plus case at right. Stream dot length is less than beautiful. Input cursor is 0 is input. Okay. Wouldn't use So if is numeric at, we have our string. Let me log here. Okay. So the first time we get this, we get, let's see, this is numeric. We're doing our number, right? So it starts at 1 here. Let me get rid of this log 2. Oh, it's building on to the string every time. Okay. So we get our stir number. Let me make sure this is out too. So 1 and 1. 1 is the cursor, so it should be 0, 1. And yet we just incremented it, so that'll be behind by 1. 10, 2. Okay, so we get to plus, and is numbers failing at plus? It's not doing expected behavior. For plus, which is plus. Let me actually log this and see why this is failing. Say this is the problem. Is known a character. Right. Why is true? Yeah. True for plus. Oh, well that's the problem. Yeah, okay. Why is this returning that char dot charcode returns the Unicode value of the character at the specified location. Yeah, of 0 is greater than or equal to. Let's see. Yeah, okay. That looks like what I'd expect, actually. String dot from charcode. I wonder if I can actually compare like that. If is number charcode at turns the number is greater than or equal to 48. Wait, is my off by a number? Yeah, it is decimal. What am I doing wrong here, Alvaro? What am I missing? 0 is greater than or equal to 48, greater than and less than or equal to 48. Yeah, there's not even a plus near around there. Char code at zero. And if ASCII number is passing number. $49, $49, $48, $43. So it's comparing it. 43. Oh. Oh my god, I'm so dumb, dude. Okay, the reason is because I'm looking if my ASCII number is greater than or equal to 48 and oh my god. Ay. I'm doing or. So any number greater than 48 or less than 57. So literally any number to infinity is returning invalid. Yeah, that explains it, actually. That really does. That's so frustrating. Yeah, there we go. Okay. Everything's working now. I was so confused there. Okay. So, I'm going to cut that out. But, okay, here we are. So, good times, good times. So, what we have here is, I'm also just going to open up the channel on a second screen so I can make sure everything's going good. Okay, sorry about that. Well done. Yeah, I wish it didn't take so long. I really do. Because I knew that worked. Okay, so we have our tokens, right? So now we can actually get onto parsing. Yay. Let me verify that invalid tokens work too, right? We don't want them to work, but let's make sure they don't. So let's do something like this, right? So let's throw in a token like a semicolon. We have no clue what a semicolon token is. So what do we get? Expected a valid token at position 12. Beautiful. Let me also log out what token it is. Instead received this dot at. Right, we're just gonna say, hey, yep, instead received a semicolon. Beautiful. Okay, what about something like \n, true, I don't know. So a t is a token that we won't understand, right? So if you're actually making a language, right, or you want to add stuff for like sine, cosine, right? Say you want to be able to do stuff like this, right? Sine of 10, right, or something like that. I don't know, like sine of 1, right? Say you want to do something like this. This is going to require you to parse characters, aka identifiers, right, and parentheses. But the idea is the same. I'm not going to go into it. If you want later, I actually can once we're finished with this. But the idea is the exact same, that just like here, how we're parsing a number until we continuously get numbers, right? Well, if we were parsing a string, or a identifier, sorry, we would continue until we're no longer hitting alphabetical characters or allowed identifier characters, right? Like dollar signs, underscores, stuff like that. Same thing, if we wanted to parse a string, like an actual string or a comment, we would continue on until we're no longer in a string, aka until we hit an end closing parenthesis or bracket, right? So for that, we actually have our working tokenizer, and I'm just going to leave it at that. So now that we have a working little tokenizer, let's actually get to the fun part and implement a parser for this. So what we're going to do is inside of here, I'm going to create a parser function, right? So we're going to do class parser, parser, if I can spell, there we go. It's going to take in the constructor, we're just going to take in the tokens, and that's literally going to be it, I guess. Yeah, I'll just do that. So we're going to do tokens. Actually, we're going to create a scanner, right? Scanner is going to be a new scanner, and we haven't created this yet, but we'll do this basically in the constructor, I guess. So we're gonna have a scanner, which is basically just a class for scanning stuff. So we're gonna do this dot scanner is equal to a new scanner. And the only reason we're creating this is we want a way to easily traverse our array of tokens. C-A-N-N-E-R. There we go. And that's basically it. We actually, for something so basic, we don't even need that. We're just going to literally create an at method and a peek method, I guess. So we'll just do that, right? So we'll do at, just like our previous one, is going to return. This is going to be tokens. Tokens is equal to an array by default. This dot tokens is equal to tokens. Beautiful. Return this dot tokens dot at this dot cursor. We're just literally going to kind of do the exact same thing we were doing before. Typically, you'd want to add a lot of abstraction over this, right? But this is a very basic tutorial. So we're going to have our at method. We're also going to have a method for peeking, which you'll see is pretty useful. We're going to have like a method so we can look at the next token, which is just going to do return this dot tokens at the cursor plus 1, right? And we're going to have n, which is just by default equal to 1, and so we can look past n. We're never going to need to look past anything else, but in some recursive descent parsers, you might actually need to look past more than 1. And then we're going to have a advance, or en each token, we'll call it each token, and it's going to take in the token type, right? And we're just going to take that, and we're going to eat the token. Hashtag at cursor in line 6 and 10. At cursor 6 and 10. Right here. Are you asking what the hashtag's for? Okay. So while I'm waiting for a response from you, I'm going to continue with this. But what we're going to do is we're going to get this token type. And the whole point of an eat token function is to verify that we're eating the correct token, right? So if we want to advance the token, they're missing. Oh, yeah, I do stupid stuff like that a lot. Thank you. So if we want to advance the token, we want to make sure that this is of the correct type, right? So if we're expecting a number, then we would expect this to be a number token. So what we're going to do is up in here, we're actually going to const token type I think it is. Let me actually check. It's in our lexer, right? Token types is our constant is equal to require lexer. Right? And we just want this constant so we could check if they're the same, right? So we're going to say if token type is we want to do if token type is equal to this dot at, right, dot type, then we know we have successfully found the token, right? So if it is, we're just going to do this dot cursor plus plus, right? And then else we're going to want to throw an error. And we're again going to do some template stringing. And we're going to say, well, we expected the token type to be right, something else, but it wasn't. So that's not good. So token type. Instead received this dot app type, like so. Okay. And that's all we're going to do for our eat function, right? So that's actually it. This is all of the methods inside of this for helper functions. I'm just going to get rid of these real quick. Didn't miss any hashtags. Beautiful. So that is that for that. Now we're actually going to get started with actually parsing this. And one thing to kind of branch off at is when we're parsing these types of things, right? Right now we have, if we actually go back in here, right now we have a type of integer, type of plus, a type of integer again, minus, things like that. What we're going to want to do is actually check what type these are and basically parse the left-hand side first, right? Because typically there's left precedence. So let's actually just get started with that and create a function called parse expression, which we're also going to have parse as a function, which is the only public function in here. And that's basically that. It's going to take, and it's just going to do return this dot parse expression. So this is what we're going to do. We're just going to parse, and we're going to return a parse expression, because all of our code that we're going to pass in here is our expressions, right? They're not like if statements, while statements, function declaration statements, right? We're only dealing with expressions with these little types, right? So we're just handling arithmetic. And one thing to keep in note is if we want to handle order of operations, you kind of want to think we want to handle precedence. And the multiplication, this side is going to take precedence over this side. So we want to basically we want to parse this side before we end up parsing this side. And one way that we're going to do that is by having 3 different types of parses, right? So we're going to have a parse factor, which is going to parse. This is going to be the highest precedence. Highest precedence, right? And here we're going to be returning our actual numbers or our strings or identifiers, things like that. We're going to have a parse term, which is going to be basically parsing the multiplication, the division, things like that, right? So this is going to be the term is going to be like parsing multiplication. And in here, we're going to have a parse. Actually, that's it. You would have a third one if you were parsing equality operators, right? They have less precedence than addition, subtraction. In here, we're going to parse addition, subtraction. And above that, we would also have one for parsing like equality operators, things like that. This was natural language. But since we're not, we're going to just do that. And what we want to do is we basically want to say, okay, this is the least precedence in expression. A term takes more precedence than an expression, which is just addition, subtraction. A term might be addition, subtraction, multiplication, division, and a factor might be all of those and the actual numbers themselves. So what we want to do is we want to do let for the expression, right, or the left-hand side, the we're going to say the left-hand side is equal to this dot parse, and we're going to go to the lexed term, right? So what's going to happen is, let's imagine we have this. This is our code. It's just the number 1. What's going to happen is it's going to say, okay, parse this, right? Parse the left-hand side, aka just parse the numeric literal 1. That's going to come into here, and we're going to do the exact same thing. We're going to do let LHS, right, for left-hand side is equal to this dot parse. And this time, we're going to do factor, right? We're going to go one step lower than we already are. And this is going to be 1 again. So we're going to get 1 in here, right? 1's going to be in here. And now, of course, man, you have a good day. And now we are going to actually handle our numeric literal, right? So if we get to this point, parse factor, then we know with absolute certainty that we are at a numeric literal, right? So we can say, okay, we're at a numeric literal. Let's handle that. So we can do return a numeric literal, right? So we're going to just return the type. Type is numeric literal, and we'll just pass this in a string like so. And we're going to say the value is this dot at dot value. And this is going to be our numeric value. And actually, we're just going to say let literal is equal to so, like that. And what we're going to do is we're going to then eat our literal token, because we're expecting this to be of type literal, right? So we're going to do this dot eat token, right? And we expect a token types dot number, or an int, right? Integer in here. And then we can return the literal, like so. So by simply doing this, in fact, we're just going to do this for now, right? So we're just going to return the left-hand side, and we're going to return left-hand side like so. And this is actually going to be valid, and it should parse as we would expect. So let's kind of run through it. We're going to parse an expression, and for our basic expression, we're just going to parse the number 10, right? So what we expect to get back is a numeric literal token where we have the number 10. So let's actually run this and first bring in our parser. So we're going to do const parser is equal to require dot slash parser, like so. And then in here, we are going to say const parser is equal to a new parser, right? And we're going to pass in our tokens, which I sadly defined below. There we go. There we go. Okay. And then in here, we're going to do const ast is equal to parser dot parse. And I think I didn't export parser now that I think about it. I didn't, yeah. So we're going to do some module dot. There we go. And I think this should now be good. Welcome to the stream. Okay. So if I look at this, right, we would expect parser takes in an array of tokens. Beautiful. So let's actually run this and see if we get any errors. And what do we get back here? Right, so we didn't get any errors. We have our token type of integer and the EOF. So let's actually see if, instead of logging tokens, let's log the AST and see what we got out. And you can see this is what we got. We got a type of numeric literal and a value of 10. Now, what we're going to do is we got to think, okay, what if we didn't want to just parse one number, right? If we want to do 10 plus, say, 3, how would we go about parsing this now, right? Because right now, in our parse function, we're parsing an expression, and then we're just going down the left-hand side. So we're never actually getting to that plus token. How do we go about getting to the plus token? And that's where we take this. In this parse expression, we're parsing a additive or subtraction, right? We're going to look for those tokens. So we're going to continue down the left-hand side because we still want left-hand side precedence. So that way order of operations is followed. But what we're going to do is we're going to do while this dot at dot type, right, is equal to token types dot plus, or this dot at dot type is equal to token types dot minus, right? We're going to say, okay, while it's one of these tokens, right, we want to actually parse again. So this is going to handle the case where we have a plus token or a minus token. So let's imagine this case, right? It's going to say 10, boom. We already parsed that right here. Now we've already eaten that left-hand token. So we're at a plus token. Okay, well, what do we do? Well, we can say, okay, the RHS is equal to, and we'll do let RHS for the right-hand side is equal to this dot, what would we do, right? Well, what we're going to do is we're going to do parse expression, right? And what we want to do beforehand, and this is very important, is we want to eat this token because we know our current token, right, is this. So we're going to do this dot eat token. I'm just going to do a weird cheaty hack where we do const t type is equal to this dot at dot type is equal to token types dot plus. If it is, then we'll do token types dot plus. Else we'll do token types dot minus. I'm just gonna do a cheaty kind of thing like so. So we're gonna do the TT type, right? So we're gonna eat the token. So we're gonna eat our current token. We are going to then parse the right-hand side of this expression, which is going to set us back into the same kind of loop, right? We're going to have another parsing kind of thing. And I'm kind of looking through my notes real quick. I'm sorry. I want to make sure that I don't mess this up. Okay, I think that's good. Okay, so we're going to parse the right-hand side of the expression. And what we're going to do is we're going to say, okay, the now new left-hand side, because again, we might have another token, like in this case, we have a minus, so we want to also parse that. So we're going to say the new left-hand side is equal to, and we're going to have a type attribute of binary operator. And we're going to put that again in quotation marks. We're going to have a operand, right? The operand is going to be the this dot const token operator is equal to this dot at dot value, right? The operand is going to be actually we'll just do this with the operator, right, like so, and then we're going to have a left-hand side, which is again going to be this left-hand side right here, and the right-hand side, right, is going to be the RHS. Boom. And now we have this recursive structure. We have we're calling parse expression on this thing itself, which is going to send us back here, and then it's going to parse. So it's going to do 10, right? We're going to parse the value 10, get sent in here, and here. We're going to come back with the numerical literal 10. Then we're going to be at 10, right? We're going to hit this plus. It's going to get the operator, the value. It's going to eat the plus token, and then it's going to parse the right-hand side, right? And that's going to get a 3, okay? It's going to do the same thing. We're going to come back, and then we're going to get another minus token. But we'll have a left-hand side being that 10, the 3, the plus, and it'll continue going like so. So this is actually our parse expression function. And I'm just going to copy this because the parse term is basically identical to this. Instead of doing parse term in here, we're going to do parse factor, right? So we're going to get the left-hand side by parsing the factor. This is going to be the same thing. We're going to get the right-hand side by parsing the expression. The binary operator here is going to be the same, and here, everything's going to be the same. But what instead we're going to do is we're going to change this to divide and multiply. Right, so we're going to do divide, and here we're going to do divide and multiply. Okay, so let's actually see if first try I was able to get this to work. I have little hopes for myself and my programming abilities, so let's see. Okay, we kind of got it. But you can see that this is already kind of producing that tree structure we'd expect, right? So we have a type of binary operator. The operator is undefined for some reason. We're getting a left-hand side of a numeric literal, right, which is 10. And if we look, that's correct, 10. And a right-hand side should be 3, that operator, and 3. And if we look back, we actually see that that's what we get. We get that. Now, the question then is, why is the operator not working? And once we get that, let's see if it follows order of operations. And so the operator is this dot at, oh, it's a function call. That is why. It's because I do not know how to write valid code. There we go. And there we go, right? So we could see the type is a binary operator. The operator is plus. And the left-hand side is another kind of value, right? It's a numeric literal. The right-hand side is a type, right? And yeah, so let's actually try adding more depth to this, right? Let's say we make this multiply, right? So what we expect here is this left-hand side to be a little bit heavier, right? Or we expect it to go 10 plus, and then we expect this kind of tree structure. Let's actually see if this works. I think it will. Okay, so we get 10 plus, and the right-hand side is like that. Let me actually kind of plus 3. And let's just see how this looks now. So we get the type is plus. It's a multiplication between another two types like that. And I think that's actually, I think that's correct. Let me verify this. I think that would be correct though. 10 plus 3 times 3, is it playing precedence to the times 3? Let me make sure it is. I think it is. Okay, so we have the plus operator. Let me see. It should be 10. The left-hand side is going to be 10. And the right-hand side, yeah, needs to be that. But if I do, I guess the best way to test this would be to actually add parentheses and see how it handles this kind of thing, right? So let's actually get to this last thing where we add parentheses, and this is basically a parenthesized expression. And the way you can kind of think of it is what we'll do is we'll just run it and see what happens, right? First thing is it's going to say, okay, we don't know what this parentheses thing is, right? So it understands the pluses, the minuses, and all those types of tokens. But inside of our lexer, we haven't actually done anything to look for a parentheses token. Conveniently, it's a one character token, so it's super easy to add in. So I'm just going to add another case, and this time we're going to have a left-hand paren and a right-hand paren, right? We're going to have a right hand, a left hand, and the types, we're going to create two new types for L paren, and we're going to set this equal to L paren and R paren. And this is going to be like this, R, like so. And in here, now we can do, okay, well, this is a token type dot L paren, and this is a token type dot R paren, right? And that actually should give us valid tokenization. So let's just run this and make sure. And beautiful. And what we see here is expected a token to be of type integer, instead received type of left parenthesis. So that's because inside of our parser, when we get right here, right, we expect the token to be a valid integer, but it's a parenthesis. So we're just going to do a little if check. If this dot at dot type is equal to a token types dot integer, right? Then we're going to do this, because then we know that the token we've gotten to this point is a valid integer. And we're just going to return the literal, like so, right? And else, at this point, we know that we are at a parenthesis, paren. We should be at a parenthesis expression, which means we're expecting the current token to be a left parenthesis token. So we're going to do while this dot at, and we're going to get the token, right? So we're going to do this dot at, while this dot at dot type is equal to a tokens type dot L paren, while this dot tokens dot at dot type, let me actually get here and see what we're getting, right? So it's console.log this dot at, right? Because I actually forgot what type of token should we be getting right here, and I'm just gonna get rid of that. And let's I'm just gonna process dot exits. Actually, we're just going to yeah, we're just gonna return out of there, and in here, let's actually test out what we get, right? So 10 times 10 plus 3, we would expect a left paren token, I think, to be our current token. Let's say. So yeah, our type is left parenthesis token, which means we need to actually eat this token, right? So at this point in time, we know that we've received a left parenthesis token, so we actually want to eat that. So we're going to do this dot eat token, and it's going to be of type token types dot L paren, right? And now we can check, we can do our while loop, right? We're going to do while this dot at dot type is not equal, or is not equal to a token types dot R paren, right? While we're not at a right parenthesis token, what we're going to do is we're just going to say let expression, right? We're just going to set it to something blank by default. We're just going to say expression is equal to this dot parse expression, right? And then at the very end, we're just going to return expression. And this will handle our right parenthesis, left parenthesis grouping. I'm pretty sure, let me think through. Yeah, I think this will handle everything we need. And while we're not at the type of right paren, which means we do need to eat our right paren token, right? So we need to do this dots eat token types dot right paren. And I think that should be good. Yeah, okay, so here's what we're getting, right? We are getting this. So we have type of binary operator. The left-hand side is a multiply, right? So we do 10 times that result. And let's actually see how it handles internal things, right? So -3 plus 4. Let me just do a multiplication here. Okay. So something like this. I forget. Yeah, I think I'm going to need... yeah, but what you see is it continues with the order of operations and our parse tree. And I think there is a JavaScript function that actually prints like the characters. Let me actually look that up. So it's JavaScript and print object depth, I think. No, I don't want. I know there's a default function name like log depth, right? Is it? Oh, is this it? Util. Oh, it is this. Okay. So it's console. So we bring in util.inspect, something like this. I'm just gonna yoink this. You know, no shame. I didn't even know there was a library. Good to know. So util inspect, the object we want is AST, and I'm going to shamefully yoink that code and hope it works. It does. Wow, that is amazing. So what I'm going to do is true to enable color. So it looks like depth, false, null, and true. Okay. Okay. Nice. So we can see that now we have this pretty interesting kind of thing where we have this right-hand type recursion, right? Where we have our binary operator, right? The left-hand side is the value 10, while the, oh, I am getting an error I'm noticing. Oh, no, I'm not, 10. Okay, phew, I saw 2 10s and I got really scared. But here we could also say group this, and let's just group these two together, right? Let's see if that works, right? So parentheses inside parentheses, we would expect to now produce a different result, and we do. So we get our right-hand side, which is a binary operator with the type of plus, right? So it's 10 plus we would expect the right-hand side to be a multiply operator. Now let's see if that's correct. The right-hand side here is a... Wait, is that correct? I don't actually think that's correct. I think I messed up the order of operations. Let me make sure. So let's just do this. Let's see what we're getting out of this. So we have a times operator. That makes sense. 10 is our left. The right-hand side should be this whole thing, which means right-hand side should be a plus operator between 10 and 3 times 3, where the right-hand side is 3 times 3, And in here, I'm just going to add a divided by 2 and just see how that affects everything. And yeah, okay, this is very correct, right? So we get left-hand recursion when it's a priority. So in this case, we want to evaluate 3 times 3 before we do divided by 2. And that's where we can actually see we have a right or a left-hand recursion, right? So it's recursing on the left-hand side instead of the right-hand side like it traditionally does, which is what you would expect from parentheses. Same as if I just made this multiply and this a minus, I would expect that exact same type of structure. And we don't get it. Okay, so I am not following order of operations with this because we should see the left-hand side, right? It should go 10 times this expression, which we know we're getting. And then we should have a plus operator, where the right-hand side is a multiply operator. Oh, I guess it is, actually. 10 plus, I think that's correct. Parse term. Yeah, let me actually look at this example. I think that should be... Yeah, I think that looks correct. And one way we can verify this, I figured, without actually looking in a book, is actually using something called AST Explorer, right? So let's actually see how the JavaScript interpreter looks like, right? So let's do AST Explorer. We're almost done. I think I just have a small issue, but let's see, right? So here's the AST for JavaScript, right? And you can kind of see what it's doing. There's different nodes, declarations, identifiers, literals, right? And what we want to do is take our expression that we're doing in here, that we're trying to parse, right? So we are trying to parse this bad boy. So let's see if we get the exact same results as AST Explorer does, right? So they get an expression statement. We're going to ignore that, right? Okay, the first thing we care about is this. They have a binary expression where the left-hand side is a literal of type 10, right? Hide methods, hide location data, hide type keys, yes, hide empty keys, and that looks literally beautiful, right? There we go. Okay. So we see we get a binary expression where the left-hand side is 10, and the right-hand side is a binary expression with minus. So let's look through here, and let's just pull this up right next to it. And look at it like so. Okay. So what we see is we have a binary expression of 10, the multiply, and a right-hand binary expression, right? So we get multiply, left hand is 10, a right hand is plus. So I did mess this up. Good to know. Oh wait, no I didn't. 10 plus 3 times... Yeah, I'm supposed to have a minus, and the left-hand side is supposed to be a binary expression, where it then is 10 plus. Okay, so that's actually good to know that it's not following order of operations here, but with the parentheses it is. So let's actually see what's going on. When we parse our terms, right, we're getting our plus, our minus. I think I'm supposed to do parse term. Or parse term, am I supposed to do? Like so. Let me actually just run this and see if it's... No, it's parse expression. And yeah, it's what we were using before. And we want to do what? This is the right-hand side, right? And Is this what we want? I'm trying to think. Do we want to go down the left-hand side first or the right-hand side first? Let me think about that. We need to... I'm going to pull up some... Oh, I don't have it on my system. Yeah, so right here, we're going down the right-hand side, and then we parse expression. I don't think that is the correct solution. I think I'm supposed to parse maybe the left-hand side first. Let's see. I'm trying to think. Okay, so with a term, okay. Okay, I think I'm actually supposed to do, in this parse expression, I'm supposed to parse a term, because we want the lower precedence one. This is beautiful, I think, right? Is this factor? So this is, oh, the left-hand side is, parse a factor, right? So yeah, we want to parse the term in the left-hand side. And then in here, we also want to parse a term. And that makes sense. Okay, that makes perfect sense. Which means in here, we don't want to parse an expression, we want to parse a factor. And that is what the issue was. Which means in here, we're parsing a factor. Beautiful. And then inside of there, okay, we want to check if we're at our numeric literal, right? Is that what we're doing? Yeah, type. And then we have our token types. And then, oh, we don't want to do while. We just want to do an if, I think, right? We just want to check if we're at a left paren, right? We just want to, yeah, if this is a, because it'll parse it on its own. If type is equal to token type right paren, expression is equal to this. First I eat the token, I guess. I eat the left paren token. We're gonna eat that here, not in there, because that's kind of dumb. So we're gonna eat the left paren token, right? And then we're gonna say what? We're gonna say if we're at a left paren token, then we parse it after eating it, right? So we just return this. I think we just return this. Yeah, return the whole expression. And then that's that. And then if in here, we're just going to throw an error, I guess, because I have no clue why. If we're at a left paren token, then we need to eat it. Then we need to parse it, and then we need to eat this dot eat. Eat the token types dot rparen, right? Oh no, rparen. And what am I getting an error for? Oh, let expression equal this, and then we're just going to return expression. Beautiful. That's beautiful. Else, right, if we get to this point, then something's wrong. We're just going to throw an error, I guess. Expected a instead received, wait, what did we receive? Well, just do a JSON dot JSON, oh. Dot stringify of our this dot at, right? I'm just gonna say, yep, that's where we're supposed to be. Okay, that should be beautiful. Now let's try it. I actually think this will work. I have high hopes. Oh boy, that is vum today. I don't understand, Mari. Expected a parentheses. Oh boy, expected a parentheses token or an integer in input received. Type left paren. What? Oh, this is supposed to be an L. Left paren. We're looking for a left paren token. Jesus. Oh boy. Oh, this looks right. Wait. This looks like a valid parse tree. Wait a minute. Did I actually get it right first? I guess like 8th try. Let's see. Let's compare the trees, right? 10 times, they're the same inputs. Beautiful. Okay, so we have binary operator of multiplication, right? Let's just open up all of these, I guess, a little bit. Okay, boom. Okay, so this is what our tree, I guess, should look like. We should have, oh no. Okay. So we have a multiple, oh, it's so awkward. Oh, it keeps closing. Okay, that's fine. So we have a multiplication operator. The left-hand side is the value 10. The right-hand side is a minus expression. Beautiful. I can already tell that's doing good. With the left-hand side of this being a plus operator, with the right-hand side being a multiply 3 and 3. So what are we getting here? We're getting the operator is like this, right? So the left-hand side of the subtraction should be a plus operator of 10 and a right operator, so plus operator of 10 and a right operator of multiply 3 and 3. Please be correct. 3 and 3, yes. And then this is 2 under the minus. Under the minus, yep. Okay, so that took a little bit longer than I would have liked, but we have a perfectly syntactically valid way to parse a tree format, right? So we can parse this and we can handle order of operations. We can do things like that, right? So if I do 10 times 2 plus 3, actually we'll do times here. We'll do minus here, right? So with this expression, we would expect the left-hand side to be this, right? Wouldn't we expect that? Let me actually see. Yep, so the left-hand side is the literal. Okay. Yeah, that makes sense. The right-hand side is a binary expression. Let's do it instead, like so, where we now group it, right, using groupings. So 10 minus 2 times 3. What do we expect, right? The left-hand side is a binary expression. 10 and 2, and the right-hand side is 3. Okay. And if we run this in here, oh, actually, it's changed the inputs. 10, I already forgot what I did. 10 minus 2 times 3. 10 minus 2, I'm just going to add a whole bunch of spaces. So it doesn't really matter, times 3, right? And then here, we get multiply. The left-hand side is a binary operator with a minus 10 and 2 and a value of 3. I think we have done it. 10 is the left, right is 2, multiply of 3. Yep, that looks beautiful. Okay, Thank you for following along with me. This was actually really long, an hour and 45 minutes. But I think that we have this, which means in another episode, or I'm just gonna do another live stream some other time, and we'll actually run this, right? So we'll take this beautiful tree we've created and actually do something with it. So we'll actually be able to evaluate any mathematical expression similarly to the eval method, right? So if you passed into JavaScript something like this, const result is equal to eval, I think, yeah, eval. We do 10 minus 1, 0 minus 2, right? And we console.log results this time. What we'd expect is, obviously to get 8. And that's actually what we'll get, what you'll see. So we just have to evaluate that. We're going to basically create an eval method, which instead of taking in 10 minus 2, it's just going to take in our AST, right? It's going to take in our abstract syntax tree, and we're basically going to be able to go recursively parse it and actually handle the arithmetic that's required to do so. So I hope you found this video slash stream fun. Thank you for sticking around. I think it's Mari. Yeah, have a good day, and I'll talk to you guys later. And unless you have any questions, I guess I can stick around for a few minutes. Okay.